Okay, so we are now on lesson 23, and this lesson is just basically going to be an introduction to electrostatics. Our focus is going to be mainly on Coulomb's law. So our learning objectives is that at least by the end of these lessons, or at least the next 3 lessons in which we're going to be dealing with electrostatics, you should be able to state Coulomb's law, which says that the magnitude of the electrostatic force exerted by one point charge, and that charge we call it Q1, on another point charge which we call Q2, is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance, and that distance we call it R between them. Additionally, you should be able to solve problems using this equation. So this is just the mathematical symbol of Coulomb's law for charges in 1 dimension, and you'll see how we do that, as well as for charges in 2 dimensions. Okay, let's just go. And then the other thing would be that for charges in 2 dimensions, and let me see. And then for 3 charges in a right angle formation, you're gonna do a problem like that earlier. So, and then you have to limit charges at the vertices of a right angle triangle. So that is basically what we're going to be focusing on this lesson. In the upcoming lesson, we're gonna talk about electric field strength, but for this lesson, our focus is just on Coulomb's law. So yes, let's just get straight into it. So we are here and we're talking about electrostatics, and our focus, like I mentioned, is really going to be on Coulomb's law. So you were introduced to electrostatics, I believe, in grade 10, and so we're going to do a little bit of revision where we're going to talk about the principle of conservation of charge, which you should know what it is. And the principle of conservation of charge basically states that conservation of charge basically states that the total charge in an isolated system remains constant, or that it is conserved. What does this mean? This means that when two charges are made to touch, so for example, if you have a charge here, we call it Q1, and then you have another charge Q2, and these two charges are made to touch, so you're bringing them closer together. The total charge on them is shared. So let's say this had a charge of 2 and this one also had a charge of 2 coulombs, right? And then you bring them together. So if the total charge between them is shared, and if the 2 conductors are identical, such as this one, and then if they are identical, then each charge will then at the end, so we'll have a new charge Q new will then be just a half of the total charge. So what does that mean? That means we have Q1 plus Q2 all divided by 2. So now that the new charge on, okay, maybe I should have used let's say 4 coulombs here. So we have 2 plus 4, which gives us 6, meaning this is 3. So now the new charges on this sphere after they are taken apart will be 3 coulombs. So that is just the thingy, an important equation for you to know about the principle of conservation of charge. So that new charge will just be a half of the total charge. So we add Q1 plus Q2, we divide it by 2. All right, and then another thing is just the principle of charge quantization, which states that the charge on any object is an integer multiple of the elementary charge. So what is the elementary charge? The elementary charge is given by QE, and the value of it is minus 1,6 multiplied by 10 to the power of minus 19c. So this is the symbol for, or the symbol how we represent the principle of charge quantization in symbols, where this is just the charge and it's measured in coulombs. This is the elementary charge, which of course we already mentioned it's given by this value, and this will just be the number of electrons. So those are just some important things to know from grade 10. But now let us actually now move our discussion to Coulomb's law. What does Coulomb's law say? We've already mentioned it earlier that Coulomb's law says that the magnitude of the electrostatic force exerted by one point charge on another point charge is directly, so we have 2 point charges of Q1 and Q2, and they exert a force on each other, and that force is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance r between them. So this is that Coulomb's law in symbols. This is what it is saying. So let us now define what each of these things mean. So F is the force of attraction between the two charges, and we know that force is measured in newtons. So this is the force, the electrostatic force. So this will be the electrostatic force in newton. And then this we call the Coulomb's constant, and the value for the Coulomb's constant is 9 multiplied by 10 to the power of 9 Newton meters per Coulomb squared. So that is it. And then this is just the charges, the respective charges that we are dealing with. You know, it's measured in Coulomb, and this is now the distance between these two charges measured in meters. So that is just something important to know. So before we continue in terms of doing calculations, it's just very important to realize that electrostatic force is a vector. So all vector rules that we have learned already, that you know, in terms of direction as well as how to add and subtract vectors, they all apply. So very important for you to know that. So other important consideration to take when working with this formula is that, one, when you substitute the values of the charges, only substitute the magnitude. So you do not really concern yourself much about negative and positive. Just substitute. So if you're given a charge, let's say Q2 is given as -3 coulombs, only substitute just 3 coulombs. You will see how we take care of direction. And then direction, like I mentioned, is determined by the nature of the charge. So remember, like charges are going to repel each other, and unlike charges are going to be attracted to one another. And then so if we have these two charges, let's see, this is Q2, both of them will experience the same force or electrostatic force. Why? Just remember, in terms of Newton's laws, Newton's third law of motion, what does it say? So think about it and try to see if you can actually answer why would both these charges experience the same force. So now let us now take a calculation to kind of reinforce what we have learned and how to use this equation for the electrostatic force. We have an interesting question here, and it's in 1 dimension. Later on, we're going to do a calculation in 2 dimension. So what is this question says? This question requires us to calculate the resultant or net electrostatic force on the charge QB. So we have a setup such as the one that I've drawn above there. So where we have 3 charges, A, B, and C, and then the charge on on A is -2 nanocoulombs. So remember, always convert this. When we convert it, this is just going to be -10 multiplied to the power of 9 meters. So nano is to the power of 10 to the power of -9. The same thing we can do here. This will just be +3 multiplied by 10 to the power of -9 meters. And this one would be -1 multiplied by 10 to the power of -9 meters. All right. And another thing that we can do, because we see that this is the distance, so the distance between A and B is 3 centimeters. It's given in centimeters. We know that it must convert it to what is it? We must convert it to, so this R between A and B, we must convert it to meters. So then this means it's just going to be 3 multiplied by 10 to the power of -2 meters. The same thing here, centi just means 10 to the power of -10, and then the distance between B and C is BC, same thing, just going to be 5 multiplied by 10 to the power of -2 meters. All right, so that's the important thing to know. And our calculation says that we must determine the resultant or the net electrostatic force on this charge B. So the first thing was just to draw a free body diagram and say, okay, this charge is going to experience a force exerted by this force, and this force is, so it's positive, so it meaning that it's going to be attracted to A, meaning this force is going to, so the force A on B is just going to be in this direction, right? And then this one over here, this charge also will experience a force due to the presence of this charge, and because this charge is also negative, it's going to be attracted to it, right? So in this side we have the force of C on B, right? So that's how you draw the free body diagram. So this dot will just be the charge B, and then these vectors just show the charge, the force that B experiences because of A, as well as B experiences because of C. All right, so now we go back to our original equation, which says that F, so we want the force on A on B because of the force on B because of A, which will be given by K, QA, the product of QA and QB, all divided by R squared. And this is just a simple calculation. So we said that K is that Coulomb's constant, and is given by 9 multiplied by 10 to the power of 9. And then just a matter of substituting everything in there. Minus 9. The distance between this is just 3 multiplied by 10 to the power of minus 2. And then remember, it is squared. So the answer that you get, and you'll check it for me, is just 6 multiplied by 10 to the power of minus 5. And it's in newtons, remember, and we know that it is what? To the left. And we can say that, let's say that to the right is positive, and then to the left is negative. Okay, so we can do a similar calculation for that force on, so force on B by C, which will then be K QB multiplied by QC. All right, so all of it divided by R squared. Is just a matter of putting everything again. 9 multiplied by 10 to the power of 9, and then this would be 1 multiplied by 10 to the power of minus 9, 3 multiplied by 10 to the power of minus 9, all of it. And the distance between those two charges B and C, we know that it is 5 centimeters. We converted to meters, so it was 5 multiplied by 10 to the power of minus 2 meters. And if you put this in your calculator, you should come to a value of about 1.108 multiplied by 10 to the power of minus 9 newtons. And we know, according to that sketch that we drew, that it was to the right, right? And we said right is positive, then left is negative. But we're not done, because our question required us to calculate the resultant, which is the net. So the net means that we have to add the both. So we have to add the force on B because of A plus the force on B, the force on B because of C, so FCB, right? But then this is something that we know. We said that this FAB, oh, that's not in the picture. FAB is to the left, so it's going to be negative 6 multiplied by 10 to the power of minus 5, because we selected left to be negative, if we remember, and then plus 1, so we found that value to be 1,08 multiplied by 10 to the power of minus 5, and this is going to be give you a value of about negative 4.92 multiplied by 10 to the power of minus 9 Newton. It's negative. What does it mean? That value F net, therefore F net is actually equals to 4.92 multiplied by 10 to the power of minus 5 Newton to the left, right? So that is what that thing is essentially telling us. And we can also draw this in terms of vector diagrams. So we can say, okay, the force, draw the vector for the force of on A because of the force on B because of A, and then this force on C because of B, and then finally this would be our F net. So please know how to do this. I've already done a lesson on how to actually draw this force diagram, so please also check it out. Okay, so are we done? I think our next question would then be in 2-dimension. Okay, so now we're given a different configuration. So now it's in 2-dimension because we have the y as well as the x-axis. So we're given still 3 charges. The charge on A is 5 microcoulombs. So you know microcoulombs simply means 5 multiplied by 10 to the power of minus 6 coulombs, right? Even here, plus 7 multiplied by 10 to the power of minus 6 coulomb. Even this one, so the charge here we are given as, so this is Q on B is given as negative 10 microcoulombs. So which would be negative 10 multiplied by 10 to the power of minus 6 coulombs, right? And the distance between A and B is given as 10 millimeters. We know milli means 10 to the power of minus 3. 10 to the power of minus 3 meters. Here it's 15, so this is going to be 15 multiplied by the 10 to the power of minus 3 meters as well. All right. And now we have to find the resultant electrostatic force on QB. So we can also again start our discussion by always drawing that force diagram. So this would be our object of interest, and then we would have a force on B because of C. C is positive, this is negative, so it will be attracted to it. So we would have that force C on B, right? And then we will have also this force, if you look at it, because of A, they are positive, so it's positive, so this is negative, it will be attracted to it. So that force of A on B would then be faced downward. And already I think it should already tell you now something, that if we want to find that net resultant, we have to draw this vector here, or F net, as a, so it will act diagonally. So we can all agree that this side here and this side are equal, right? So I can somehow just remove this here on this side and draw it here, where we say this is F, what's FA on B. And what do you notice? So we have an angle here, theta, and then if you look at it, this now actually makes a sort of a right angle triangle, right? And if we have a right angle triangle, we know that we can actually use our Pythagoras theorem. But let us note, we're not there yet. So this is where we are. So now our first job is to find the force on A, because the force on B because of A, which will be given by K, QA, QB, all of it divided by R squared. So it's the same thing that we have done previously. Not positive 9, 5 multiplied by 10 to the power of minus 6. Where's that? Okay, 6 multiplied by 10 multiplied by that, all of it divided, the distance between them is 10 multiplied by 10 to the power of minus 3. So you put this in your own calculator, and you should also come to a value of 4,500 newtons. And we know that it is actually, so FA is actually acting downwards, so we would say down, because A attracts B, right? And C also attracts B. So we try to do the same thing again for FA, for FC on B. So we say K equals to QC, QB, right? All of it divided by R squared. So we have 9 multiplied by 10 to the power of 9. And then we have 7 multiplied by 10 to the power of minus 6. All of it multiplied by 10 multiplied by 10 to the power of minus 6. So I'm running out of space there. All of it divided by 15 multiplied by 10 to the power of minus 2, all squared. Correct. So you're gonna come to a value, just check those values with me if they are correct or not. And when you drew our force diagram, this force was acting in this direction, so it was acting to the right. Right, so now that we have our two forces, I don't know if I'm going to run out of space. Okay, so now that we have our two forces, we can now use Pythagoras theorem. So you notice that we have this side over here, the adjacent side. We also have the value for the side over here, the opposite side. So to find the hypotenuse, we simply just use our Pythagoras theorem, where we will say, so F net means F net squared will equal to F squared AB plus F squared BC, right? And then to find F net, we simply just put everything in a square root. So we found out to be 4,500 all squared plus 2,800 all of it squared, and that actually gives you a value of about 5,300 newtons. So that is our thingy, but we're not done, because we saw that this force acts at a certain direction. That direction we have to find, so hence we have to find theta. So we can't say it's to the left or to the right. We have to include the angle that it makes with respect to the x-axis, and to do that we can just simply use the tangent of theta, which says opposite over adjacent. Our opposite side here is FAB, and the value for FAB is 4,500, all of it divided by 2,800, which is our adjacent side. So this side, FCB, that we already calculated. And then to find theta, it's just a matter of the arctan of 4,500 divided by 2,800, and then you're gonna come across a value 58.11 degrees. So what does that mean? So this means that therefore F net equals to 5,300 newtons at, you can say, 58.11 degrees clockwise from the x-axis. So why are we saying that? So if you just remember your Cartesian plane, you can just do this here. So this could be 0, this could be 90, this would be 180, this would be 270, and then we are moving. So normally we will be moving in the anti-clockwise direction, so but if we're moving down, it becomes inter-clockwise. So it's that angle from 0 to about a negative of 58.11. So when you report it, you simply say that clockwise from the x-axis. And I think this actually brings us to the end of this lesson. In the next lesson, we are going to be talking about electric field strength. So thank you so much for watching.